हो गया ना स्टार्ट. Wait, I have to wear the mic, right? So I have earphones. I have only this type of mic, so I'm using this right now. So I have weared the mic. Now let's go to study, right? Study first. We have to open the timer. Timer means clock. Open clock and set a 2 hour. 2 2 hour. 2 hour, right? 2 hour time save and start. इसको चलने दो साइड पे. इसको साइड पे चलने दो. ये साइड पे चलेगा, कोई दिक्कत तो नहीं आएगा ना इस पे. ये साइड पे रहने दो. चलो अभी हम लोग ओपन करते हैं बुक्स या कुछ भी होगा. क्या ओपन करेंगे हम लोग? अभी ओपन करेंगे बुक्स या ये बुक्स है. चैप्टर्स है ये पे. एनसीईआरटी का चैप्टर्स. तो हम लोग फर्स्ट स्टार्ट करेंगे किससे? हम लोग फर्स्ट स्टार्ट करेंगे यहाँ पे. फर्स्ट स्टार्ट करेंगे मैटर. फर्स्ट मैटर अराउंड अस प्योर और नॉट. इससे स्टार्ट करेंगे हम लोग. अराउंड अस प्योर और नॉट वो बाद में देखेंगे. पहले देखना है मैटर इज अराउंड मैटर इन आवर सराउंडिंग्स. इससे चलो पहले ये चैप्टर देखते हैं. क्या कहता है ये? क्या ही कहेगा ये क्या कहेगा? और ये क्या कहता है? यहाँ पे हम लोग को पायलट भी यूज़ कर सकते हैं समराइज करने के लिए. देखो ये समराइज कर देगा मेरे को अगर कोपायलट में यूज़ करूँगा तो. पूरा समराइज करके दे देगा. बोलेगा क्या है इसमें, क्या मटेरियल है. कंटिन्यू. पूरा समराइज करके मेरे को दे देगा. बोलेगा कि क्या कंटेंट है इसमें, आप समझ लीजिए. उसकी आँखों में बहता काजल हो कैसे करती. क्या कंटेंट है इसमें, आप समझ लीजिए. वेट मिनट. या टाइमर तो चल ही रहा है. तो जैसे मेरे को दे दिया हो, इसको हम लोग कैसे यूज़ करेंगे? कोऑपरेट की ओपनर रखे. पता है कोऑपरेट को हम लोग पूछेंगे. अगर कोई वर्ड या किसी चीज़ समझ नहीं आ रहा है यहाँ पे तो हम लोग उसको एग्जैक्टली पूछेंगे, ये बताओ हमें. इसलिए कोऑपरेट यहाँ पे ओपन कर लिया हम लोग. यहाँ पे को समराइज कर दिया पूरा टॉपिक. इतनी छोटी चीज़ में समराइज कर दिया. और कुछ नहीं इसमें जो समराइज कर दिया हम लोगों को. कितना पेजेस का चैप्टर है देख रहे हो? कितना पेजेस का है ये है तुम्हारा 13 पेजेस का है. 13 पेजेस का है. स्टार्ट करते पढ़ना. क्या बोल रहे हैं? 9-10 चैप्टर भाई. 9-10 का केमिस्ट्री पढ़ रहा हूँ मैं अभी आज. 9-10 का चैप्टर अगर कोई भी आप गणित नहीं समझ आ रहे हो तो 9-10 तक आपको पता होना चाहिए. बेसिक. बिकॉज दिस इज द बेसिक NCERTs, right? You have to learn NCERTs. So first क्या बोला है? फर्स्ट बोला है चैप्टर 1 मैटर इन आवर सराउंडिंग्स. So matter in our surroundings, right? So as we look at our surroundings, we see a large, we see a large, we see a large variety of things with different shapes, sizes, and textures. Everything in this universe is made up of material which scientists have named matter. So scientists have named matter. Scientists. So here, scientist. What did the scientist do? Scientist name matter how. As we look at our surroundings, we see a large variety of things, like different things like stones, 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 or other things, right? Food, cloth, everything, and textures. Everything in this universe is made up with material which scientists have named. Everything made up with material, right? Like this lights, like clothes, like food, like our body, everything surround you see, these are made up with some specific material. Specific material, or we can call it a material, which scientists have named, which scientists have named as a matter. So the air we breathe, the food we eat, stones, clouds, stars, plants, and animals, even a small drop of water or a particle of sand, everything is matter. We can also see as we look around that all things mentioned above occupy space and have mass. In other words, they have both mass and volume. Sorry. So since early times, human beings have been trying to understand their surroundings. Early Indian philosophers classified matter in that form of five basic elements. The punch, the punch, pancha tattva. Have you ever heard the pancha tattva? Air. So what are the panch tattva? Panch tattva basically means, panch tattva is, we call panch tattva for five elements. We also call it a panch tattva or five elements in earth. Five elements. What are the five elements in this planet? So first is air, second is earth, third is fire, and sky and water. These are the five elements or five tattva: air, earth, fire, sky, and water. According to them, everything living or non-living was made up of these five basic elements. So in this book they are saying, according to them, everything living or non-living was made up of these five basic elements. Ancient Greek philosophers had arrived at a similar classification of matter. So modern day scientists have evolved two types of classification. Modern day scientists evolved, because you know that previous scientists, like in 90s scientists, they are don't have they have don't access of new technologies or new materials. They didn't get that, but now the scientists have more evolved in the with technologies and new matters they are finding out because of technology, obviously, or also the modernization in the world. So that's why they say modern day scientists have evolved two types of classification of matter based on their physical properties. Two types classification. So and chemical nature. So in this chapter we shall learn. So in this chapter we about to learn about matter based on its physical properties or chemical aspects of matter. Will be taken up in subsequent chapter. So so what activities, these are activities, and here 1.1 physical nature of matter. So physical nature of matter, then 1. So this topic name is physical nature of matter. Okay, so 1.1. So matter is made up of particles. Okay, matter is made up of particles. For a long time, two schools of thought prevailed regarding the nature of matter. So one school believed matter to be continuous like a block of wood, whereas whereas the other thought that matter was made up of particles like sand. Okay, so let us perform an activity to decide about the nature of matter. Is it continuous or particulate? So what we are going to do, we're going to do an experiment to find out that it is a like sand, particles like sand, or like a block, big wood block. Which is it? Now let's continue the activity. So activity 1.1, take a 100 ml beaker, fill fill half the beaker. So here we are taking, so I have a pen here. So we are taking this activity, right? The activity says take a 100 ml beaker. So we are taking a 100 ml beaker here. Here the picture is shown. This is the 100 ml beaker, right? So this is a 100 ml beaker. Fill half the beaker with water. So here filling half the water up, and mark the level of water. So here water level marked. But now dissolve some salt. So we are giving some salt here, like 1 spoon of salt. We are mixing here salt, sugar with the, or also you can add sugar. Observe any change in water level. Observe any change in water level. So I didn't think there is any change of water level. No change in water level. So they are saying observe any change in the water level. No, I don't think there is change in water level. What do you think has happened to the salt? I think the salt basically mixed with water. So we cannot, salt are mixed with water. So where does it disappear? Does the level of water change? Uh, these are the questions. So in order to answer this question, we need to use the idea that matter is made up of particles. What was there in the spoon? The salt of sugar has now spread throughout water. This is illustrated figure 1.1. So this is the figure. So we're adding salt here, right? So adding salt in water, but water level never changes. Why? Because particles of water are magnified millions of times. Okay, so when you dissolve salt in water, the particles of salt get into a space between particles of water. So assume, so I am showing you, assume here, assume this is the beaker, right? So this is the level of water here present, and I am adding one spoon of one spoon of one spoon of salt here, one spoon of salt here, right? So if I zoom the water molecules or particles, we can see very small in deep down water particles have this type of, say, particles have. So this water particles, these are water particles. These are, sorry for the handwriting, water particles. These are water particles. So in this water particle, there is a small gap in it. Okay, there is a small gap. In that gap, so in that gap, the salt particles are fitted. So here is a salt particle. They come up and join here. Come up and joined here. Come up and joined here. Salt particles. So that's why they are saying here. That's what they are saying. So they are saying when you dissolve salt in water, the particles of salt get into the space, get in this tiny space between particles of water. So that's why water never changed, because the gap was so small that only this type of elements only go there. Now, how small are these particles of matter? Now they are saying how small the particles of this matter. So take 2 or 3 crystals of potassium permanganate and dissolve them in 100 ml water. Take 2 or 3 crystals of potassium. So we are taking 2 or 3. So we are taking 2 or 3 potassium. So we are taking 2 or 3 crystal of potassium permanganate and dissolve them in 100 ml water. You are getting it right. So take out approximately 10 ml of this. So the SI. So here are some information given. Also, you can see the star marks here. I am zooming it. I'm zooming it. Now you can see here star marks are given because these are the important things I have to remember. So if you are in 10th or 9th class, you also have to remember this. units, because these are help with your these will help you with your numericals. So here says the SI unit of mass is, so SI unit mass of is, the SI unit of mass is kilogram, the SI unit of volume is cubic meter. Cubic meter means MQ, cubic meter, MQ. The common unit of measuring volume is liter, such that 1 liter equal to 1 dmq means dm and decimeter. This means decimeter, decimeter. This is mean decimeter, 1 decimeter cube. So 1 L equal to 1000 ml, 1 ml equal to 1 semi cube. So these are the information you have to remember it. So now take out approximately 10 ml of this solution and put it into 90 ml of clear water. So we are taking 10 ml of this solution and putting it to a 90 ml of clear water. So take out 10 ml of this solution and put it into another okay. Take out 10 ml of solution and put it into another 90 ml of clear water. Clear water, right? So keep diluting the solution like 5 to 10 times. So we have to diluting means basically when we are adding this cup water and salt in that spoon. Diluting means we have to mixing it so it can dilute means mix, you can mix properly with water. That's why we diluting means when we are doing that spoon, rounding the spoon in the water, in the clean water in the glass, that's called diluting, or also we can call it a mixing, properly mixing. So that's what they said 5 to 8 times. Is the water still colored? Now you see this, important picture. So first here is 100 ml clear water. After mixing the solution, the color changed. 100 ml color changed. But this color is changed very deeply. After diluting, after starting diluting, color is fading, right? Color is fading. See, deep color, then light color, then more light color, then they become more clear. So first time, no, that's sorry, I made a mistake. So first 100 ml clear water, then we're adding 10 ml into it, so it become colorful. Then we are adding more 10 ml. Adding, then we are diluting, right? Yes, diluting. Oh, now I understand what they have done. So first we add the solution, then we're getting a deep color of mixture. Now we are taking this mixture and adding another 100 ml of clear water. Then you can see the difference of what you can see, the difference that this color is very deep but this color is very light, this color is very deep but this color is very light. Compared to this color, it is light, right? Now we're taking 10 ml from this cup, 10 ml from this cup, and adding to 100 ml clear water. Now you can see this color is more deep than this, so this is getting lighter. Same process we're doing to this, lighter. So if this process is continuing until the, so this, if this process is continuously done, then we have getting this clear water in the last. So estimating how small the particles of matter with every dilution, though the color becomes light, it is still visible. It is still visible. It is still visible. This experiment shows. This experiment shows that just a few crystals of potassium permanganate can color a large volume of water, about 100,000 liter. So we conclude that conclude that there must be millions of tiny particles in just one crystal of potassium permanganate, which keep on dividing themselves into smaller and smaller particles. Getting it right. मारते गोली ले ले मेरी जान. Wait a minute, guys. Wait a minute. I will live. Wait a minute. I will live. Wait a minute. I will live. Oh. So now what we doing? What we do now? What we do is, so we understand the situation and the this what is this to understand this what this activity, right? Now, so we conclude that that there must be millions of tiny particles in just one crystal of potassium permanganate, which keep on dividing themselves into smaller and smaller particles. The same activity can be done using 2 ml of Dettol instead. So you can do that activity in your home. The same activity can be done using 2 ml of Dettol instead of potassium permanganate. The smell can be detected even on repeated dilution. Okay. The particles of matter are very small. They are small beyond our imagination. Okay. So now what? So now, so take 2 glasses of beakers filled with water, put a drop of blue and red ink slowly and carefully along the sides of the first beaker and honey in the same way in the second beaker. Leave them undistribute in your house or in a corner of the class. Record our observation. What do you observe immediately after adding the ink drop? What do you observe immediately after adding a drop of honey? How many hours of days? How many hours of days does it take for the color of ink to spread evenly throughout the water? Evenly throughout the water. These are the questions you can find out about if you try this activities questions. We are not going to waste time in activity questions, but directly go to the characteristics of particles in matter. So what are the characteristics of particles in matter? So particles of matter have space between them. What? Yes, characteristics of particles of matter. So particles of matter have space between them. In activities 1.1 and 1.2, we saw in activities 1.1 and 1.2, we saw that particles of sugar, salt, Dettol, or potassium permanganate got evenly distributed in water. Similarly, when we make tea, coffee, or lemonade or nimbu pani, particles of lemonade, nimbu pani also called lemonade, particles of one type of matter get into the spaces between particles. So, particles of the other. This shows that there is enough space between particles of matter. Particles of matter, there are enough space. Because when we make tea, coffee, or lemonade, nimbu pani or particles of one type of matter get into the spaces between particles of the other. This shows this shows this shows that there is enough space between particles of matter. Enough space between particles of matter. Particles particles of matter. Particles of matter are continuously moving. So these are the question. I will not waste any time here. So we will go there. So particle of matter are continuously moving. That is they possess what we call kinetic energy. Particles of matter are continuously moving. That is they possess what we call kinetic energy. As the temperature rises, as the temperature rises, particles move faster. So as you see, when we increase the temperature, like if you take one bowl of water and you mix mixing sugar in it, so you can see the sugar cubes are present in normal water. They are not diluting fast enough, but if you heat that bowl of water, you can see that that sugar cubes are melting or mixing with water instantly. That's what they are doing. That's what they are saying here. As the temperature rises, the particles move faster. Temperature rises, particle moves faster to dilute. So we can say that with increase in temperature, the kinetic energy of the particles also increases. In the above three activities, we observe that particles of matter intermix. Particles in the above three activities, we observe that particles of matter intermix on their own with each other. So they do so by getting into the spaces between the particles. So this is intermixing of particles. Intermixing of particles of two different types of matter on their own is called diffusion. We also observe that on heating, diffusion becomes faster. So why does this happen? Why does this happen? So in the above three activities, we observe that particles of matter intermixing on this their own with each other. So they do so by getting into the spaces between the particles. Okay. So this intermixing of particles of two different types of matter on their own, on their own, on their own is called diffusion. So we also observe that on heating, diffusion becomes faster. Why does this happen? Why does this happen? So they're asking, why does this happen? So why does this happen? So if we consider each student as a particle of matter, then in which group the particles held each other with the maximum force? So they are now activity. Take a iron nail, a piece of chalk, and rubber band. Try breaking them by hammering, cutting, or stretching. In which of the above three substances do you think the particles are held together with greater force? So take some take some water in take some water in a container. Try cutting the surface of water with your fingers. Were you able to cut the surface of water? What could be the reason behind the surface of water remaining together? So now particles of matter attract each other. So the particles of matter attract each other, right? So activity 1.6. Activity 1.6. Activity is 1.6 saying play this game in the field, make 4. Okay. So also they are also giving a one more activity to understand the question they ask. Why does this happen? Mixing, right? So particles of matter attract each other. Particles of matter attract each other. Now they are giving activity. So play this game in the field. Make 4 groups. So suppose or imagine like we're playing this game. So play this game in the field. Make 4 groups. So we're making 4 groups and form human chains as suggested. Forms human chain like they are making a human chain like this. Make this human chain as suggested. The first group should the first group should the first group should hold each other. First group the first group should the first group should hold each other from the back and lock arms, just like they are doing, like Idu Misimi dancers. Idu Misimi dancers. The second group should hold hands. Second group should, okay. So they are saying the first group should hold each other from the back, okay, and lock arms like Idu Misimi dancer, okay. And the second group should hold hands, okay. So first group holding like they are holding like, so if you are in a four groups, so you are holding your next person in the waist, their waist. Got it? In the second group, they are holding like hands, like chains, human chain. The third group should form a chain by touching each other with only their fingers. So the third group only touching their the next person with finger, not holding anything, so only touching. And now the fourth group of the students should run around. So now fourth group, what they are doing, the fourth group of students should run around and try to break the three, okay. Now the fourth group students should run around and try to break the three human chain, break the three human chain, break break the three break the three human chains one by one. Break the three human chains by one into as many small groups as possible. Okay, as many small groups as possible. Which group was the easiest to break? So now imagine. Now you have to imagine. Sorry, sorry. What came up? Sorry for this. Why is it coming up? Okay. So wait a minute. Wait a minute. Now what I'm saying. So which group was the easiest to break and why? So think about it. Which group is the easiest to break and why? So as you can see, which group? I'm telling my answer that which group. I think the third group is the easiest to break because they are holding, because they are distancing because they are distancing their arms and their next person, their distance, this much of distance, and they are only touching their shoulder or waist, only touching, not holding anything. So if the person come from this, they will easily break it. That's what they are saying. I'm so like, so see the answer first. So the above three activities, hmm. So the questions, what, why, now where is the and no answer is here, right? No answer is here, so I am giving the answers. So easiest way, the easiest group is to break it. The third group, then the second group, because second group are holding only hands, right? And the toughest to break is the first group because they are holding the waist, then and they are close to each others, so you can't break that type of particles. Here are some question and answer given. Which of the following are better? Hurt almonds, thought, cold, lemon, water, smell of perfume. Which are the matters? So matter you can call, they exist. They have easily remember. Which has a mass and volume, we call it a matter. Like this chair has mass and volume, but air doesn't have mass and volume, so we cannot call air as a matter. Love, this is also, we cannot call it a matter. Smell, this is also we cannot call it a matter. Hate, this is also we cannot call it a matter. But almonds, yeah, we can call it a matter. Thought, we cannot call it a matter. Cold, we cannot call it a matter. Lemon, yes, lemon water is a matter. Lemon water is a matter, yes, lemon is a matter. No, lemon water is not a matter. Yeah, lemon water is a matter. Smell of perfume, I don't think it's a now give reasons for following observation. The smell of hot sizzling food reaches you several meters away, but to get the smell from cold food you have to go close. Okay, this is the answer you have to give. So diver is able to cut through water in a swimming pool. Which property or matter does this observation show? What are the characteristics of the particles of matter? So now we are going to study states of matter. So what is the states of matter? So guys, wait a minute, I have to see something. So wait a minute, I am so wait one moment please. I have to check out something. 219 हुआ तो भी चल रहा है चेकिंग ऑल फाइल्स asylum forge Hmm. So let's continue. So states of matter, right? So states of matter. So observe different types of matter around you. So we can observe different types of matters around us. What are its different state? We can see that matters around us exist in three different states: solid, liquid, gas. So we can see three different states of matter like solid, liquid, gas. These states matter arise due to the variation in the characteristics of the particles of matter. Now let us study about the properties of these three states of matter in detail. In detail, if we are going to study in detail, so first the solid state. Collect the following articles: a pen, a book, a needle, and a piece of wooden stick. Sketch the shape of the above articles in your notebook by moving a pencil around them. Do all these have a definite shape, distinct boundaries, and a fixed volume? What happens if they are hammered? They are hammered, pulled, or dropped. Are these capable of diffusing into each other? Try compressing them by applying force. Are you able to compress them? All the above are examples of solids. We can observe that all these have a definite shape, distinct boundaries, and fixed volumes, that is, have negligible compressibility. Solids have a tendency to maintain their shape when subjected to outside force. Solids may break under force, but it is difficult to change their shape, so they are rigid. So consider the following. So what about a rubber band? Can it change its shape or stretching? Is it a solid? What about sugar and salt? When kept in a different jars, these take the shape of the jar. Are they solid? What about a sponge? It is a solid, yet we are able to compress it. Why? All the above are solids, as a rubber band changes shape under force and regains the same shape when the force is removed. If excessive force is applied, it breaks. The shape of each individual sugar or salt crystal remains fixed, whether we break it in our hand, put it into a plate, or it in jar. Sponge has minute holes. Sponge has minute. What is this? Minute holes. The food is in which air is trapped. When we press it, the air is expelled out, and we are able to compress it. The liquid state. Now the liquid state. So the collect the following. So water, cooking oil, milk, juice, a cold drink. Containers of different shapes. Put a 50 ml mark on these containers using a measuring cylinder from the laboratory. What will happen if these liquids are split on the floor? So measure 50 ml of any other liquid and transfer it into a different containers one by one. Does the volume remain the same? Does the shape of the liquid remain the same when you pour the liquid from one container into another? Does it flow easily? These are the questions. So you observe that liquids have no fixed shape but have a different volume. They take up the shape, no fixed shape but have fixed volume. Liquids, they take up shape of container in which they are kept. So liquids flow and change shape. So they are not rigid. So they are not rigid but can be called fluid. So refer to the activities 1.4 and 1.5 where we saw that solids and liquids can diffuse into liquids. Gases Gases from the atmosphere diffuse and dissolve in water. These gases, especially oxygen and carbon dioxide, are essential for the survival of aquatic animals and plants. So, all living creatures need to breathe for survival, right? The aquatic animals can breathe underwater due to the presence of dissolved oxygen in water. Thus, we may conclude, thus, we may conclude that solids, liquids and gases can diffuse into liquids. Solid liquids and gases can diffuse into liquid. The rate of diffusion or liquids is the rate of diffusion or liquids is higher than that of solids. This is due to the fact that in the liquid state particles move freely and have greater space. Why? Higher than that of solids, right? So this is due to the fact that the liquid state particles move freely. Okay. So they're saying that liquid states properties are move freely and have greater space between each other. So they have greater space. So they are saying that liquid and solid, if it is a solid, then you can see in small particles in it, right? But they have not enough space between them. They are congested, they are stick to each other. That's why they are solid, right? Because they are stick to each other then making a solid. Because you cannot create a gap, or you cannot enter in this gap, because they don't have any gaps in it, particles. But for this liquid state, this liquid, they have enough space between them, enough space. So in that space the other particles can enter can enter and can stay. That's why they are saying they move freely, they have enough space between them. That's the main difference between solids and liquid. So each other as compared to particles in solutions. So now the third one, the gaseous state. Have you ever observed balloon seller filling a large number of balloons from a single cylinder of gas? Enquire from him how many balloons is he able to fill from one cylinder. Ask him which gas does he have in the cylinder. Take 300 ml syringes and close their nozzles by rubber corks as shown figure 1.4. 1.4, okay. So that's the syringe, not syringe. Syringes and close their nozzles by rubber corks, right? As the shown figure. So here is the figure shown. This is the nozzle. What's happening here? So this is the nozzle, right? Sorry, I have to. So this is the nozzle, rubber cork, nozzle. So we are closing the rubber cork using rubber cork. Remove the pistons from all the syringe, okay? Leaving one syringe untouched. Fill water in the second and pieces of chalk in third. What? What it's saying, bro? So remove the pistons from all the syringe, okay? Remove the piston, okay. Oh, means he is saying that create a space. Remove the pistons from all the syringes, leaving one syringe untouched, okay. Fill water in the second. Fill water. Fill water in the second and pieces of chalk in third. Second and pieces of chalk in third, okay. Insert the pistons back into the syringes. insert the pistons back into the syringes. Okay, insert insert the pistons back into the syringes. You may apply some Vaseline. You may apply some Vaseline on the pistons before inserting them into the syringes for their smooth movement. Now try to compress the content by pushing the piston in each syringe. Now try to compress the content by pushing piston, pushing the piston in each other. Now try to compress the content by pushing the piston in each syringe. So piston, pushing the piston each series, pushing the piston. Here is the gas or our cork. So what do you observe? In which case was the piston easily pushed in? What do you infer from the observation? Sorry. So we observe that gases are highly compressible as compared to solids and liquids. So the liquefied petroleum gas LPG, liquefied petroleum gas LPG cylinder that we get in our home for cooking or other oxygen supplied. So we are saying we liquid petroleum LPG cylinder that we get in our home for cooking oxygen supplies for whereas in cylinder in compressed gas. So compressed natural gas. So compressed CNG means compressed natural gas, petroleum LPG means liquefied petroleum gas. Fuel these days. So in vehicles, due to its high compressibility, large volume of a gas can be compressed. Due to its high, due to its high compressed natural gas is used as fuel these days in vehicle due to its high compressibility. Large volumes of a gas can be compressed into a small cylinder and transported easily. Okay, so we come to know of what is being cooked in the kitchen without even entering there. So it so due to its high compressibility, large volumes of a gas can be compressed into a small cylinder. So we come to know what is being cooked in the kitchen without even entering there. Okay, by the smell that reaches out nostrils. How does the smell reaches out? The petroleum of the aroma of food mixed with particles of air spread from kitchen reach us and even further away. The smell of the hot cooked food reaches us in seconds. Compare this within the rate of diffusion of solids and liquids. Okay, this with the this with the rate of diffusion of solids and liquidified. Next, due to the high speed of particles and large space between them, gases show the property of diffusing very fast into other gases. So in the gaseous state, the particles move random movement. The particles hit each other and also the walls of container. The pressure exerted by the glass is because of this force exerted by a gas particle per unit area on the walls of this container of the walls of this container. So what do you observe? In which case was piston easily pushed in? What do you infer from your observation? A, B, and C show the magnificent cinematic pictures in three states of matter. The motion of the motion of the particles can be seen and compare the three. So A B C show A B C. So here A B C. This is A, this is B, this is C. So A is a solid, right? So there is no gap between them in particles in solid. The second one is liquid. Is there is freely moving and there is a small gaps between them particles. But in gaseous, there so much of a gap because each particle moves freely. So ABC show the magnified systematic pictures of three states of matter. The motion of the particles can be seen and compared in three states of matter. So now, effect of change of temperature. Effect of change temperature. So take about 15 gram of ice in a beaker and suspend a laboratory them a laboratory Harman. Take about 150 gram of ice in a beaker and suspend a laboratory thermometer so that its bulb is in a contact. So here it's showing that iron stand here. So this is the thermometer, this is the glass stirrer, this is the beaker, this is the ice cubes, these are the ice cubes, and this is the burner. So this is the first picture A, this is the second picture. In second picture you can see that ice cubes are melting and became water. So conversion of ice to water, conversion of water to water vapor. So starting heating the beaker on a low flame, note that temperature when is ice start melting. Know the temperature where all the ice has covered into water. Record your observation for this conversion solid to liquid state. Now put a glass rod in the beaker and heat while stirring till the water starts boiling. So keep a careful eye on the thermometer reading till most of the water has vaporized. So record an observation for the conversion of water in liquid state on the gaseous state. So on increasing the temperature of a solids, the kinetic energy of the particles increases due to the increase in kinetic energy. The particles start vibrating with greater speed. The energy supplied by heat overcomes the forces to attend overcomes the forces of attraction between the particles overcomes the forces of attraction between the particles. So the particles leave their fixed positions and start moving more freely. A stage is reached. A stage is reached when the solid melts and is converted to a liquid. Okay. The minimum temperature at which a solid melts to become a liquid at the atmospheric pressure is called its melting point. Okay. What is called a melting point? So here is telling a house it's called melting point, which is the minimum temperature at which a solid melts to become liquid at atmospheric pressure is called melting point. The melting point of a solid is an the melting point of a solid is an indication of the strength of the force of attraction between its particles. So it's saying that the melting point of solid is an indication of the strength of the force of attraction between its particles. Yes, the melting point of ice is 273.15 K. The process of melting, that is change of solid state into liquid state, is also known as fusion. When a solid melts, its temperature remains the same. So where does the heat energy go? So you must have observed during the experiment of melting that the temperature of the system does not change after the melting point is reached. Till all the ice melts, this happen even though we continue heat the beaker. That is we continue to supply heat. This heat gets used up in changing the state by overcoming the force of attraction between the particles. As this heat energy is absorbed by ice without showing any rise in temperature, it is considered that it gets hidden into the contents of the beaker and is known as the latent heat. The crowd latent, the word latent means hidden temple. Many pages are left? Are four. Okay. So this heat energy absorbed by ice without showing any rise in temperature. It is considered that it gets hidden into contents of the beaker and it's known as the latent heat. The word latent means hidden. The amount of heat energy that is required to change a 1 kg of solid into liquid at smoke-free pressure at its melting point is known as the latent heat of fusion. So the particles water at 0.0 degrees C to 73 Kelvin have more energy as compared to the particles in ice at the same temperature. So when we supply heat energy to water particles start moving even faster. At a certain temperature, a point is reached when the particles have enough energy to break free from the forces of attraction of each other. So at this temperature, the liquid starts changing into gas. The temperature at which a liquid starts boiling at the same atmospheric pressure is known as its boiling. The boiling is a bulk phenomenon. phenomenon. Boiling is a bulk phenomenon. Particles from the bulk of the liquid gain enough energy to change into the vapor state. So for water, is this temperature is 373 Kelvin, 100 degrees C equal to 273 plus 100, 73 K. Can you define the latent heat of vaporization? So do it in the same way as we have defined the latent heat of fusion particles in the system. That is, water vapor at 73 K 100 degrees C have more energy than water at the same temperature. 373 K Kelvin 100 degrees C have more energy than water at the same temperature. This is because particles is so this is because particles in partition this is because particles in steam have absorbed extra energy in the form of latent heat of vaporization. So solid state, if you are giving heat, it will become liquid state. If you are giving more heat, it will become gaseous state. If you do the opposite thing like gaseous state, if you give cool, it will become liquid state. If you give more cool, it will become solid state. So we infer that the state of matter can be changed into another state by changing the temperature. So we have learned that substances around us change state from solid to liquid and from liquid to gas. No application of heat, but there, there. So here is a note, one important note. So Kelvin is the SI unit of temperature 0 degrees C. 273.15 Kelvin is the SI. 0 degrees C opposite. For convenience, we take 0. Degrees C to 73 K after rounding of the decimal to change the temperature of Kelvin scale to the Celsius scale. You have to subtract 273 from the given temperature, and to convert temperature on a Celsius scale to the Kelvin scale, we have to add 273 to the hidden temperature. Sorry, we have to add 273 to given temperature. So now, are some that change directly from solid state to general state and vice versa without changing into a liquid state, are some that so in activity take some camphor, crush it and put it in a china dish. Put an inverted funnel over the china dish. Put a cotton plug on the stem of the funnel as shown in figure 1.7. 1.7. So wait a minute, I am coming back. So back with, so now, so we're here, right? So are some that change directly from solid, so we're learning this activity. Take some camphor, crush it. Camphor, camphor, okay. Camphor, what is camphor? Let's search what is camphor. Cam, uh, what is it? What is camphor? So camphor is naturally occurring organic compound cysteine H6O with a strong penetrating aroma, commonly obtained from the wood of the camphor tree. Okay, cinnamon. Okay, cinnamon. It is a widely used medicine. Okay, so it is a widely used medicine in sense as an insect repellent. Okay, crush it and put it in china dish. Okay, putting it into a china dish. So put an inverted funnel over the china dish. Inverted funnel over the china dish. Okay, inverted funnel. So this is the camper for funnel, or is the funnel? This is the funnel, right? Inverted funnel. Okay, inverted funnel. Now put a cotton plug on the stream of the funnel as shown. Okay, here is a cotton plug. Here is a cotton plug, inverted funnel. Or this is the camper. Now sublimation of camper. So now heat slowly and observe what do you infer from the above activity. So a change of state directly from solid to gas. Solid to gas. Okay, without changing into liquid state. So here is happening. So this camphor is, if we heat it, if we heat giving heat to this solid, it will become directly gas. It will become directly gas. No liquid has no liquid formed here. No liquid formed here. That's what they're saying. The change of state directly from solid to gas without changing into liquid state is called sublimation, and the direct change of gas to solid without changing into liquid is called deposition. Without changing into liquid is called deposition. So here also is a given image. I'll come in this image. So effect of change of pressure. So we have already learned that the difference in various states of matter is due to the difference in the distances between the constituent particles. What will happen when we start putting pressure in compressed gas? We have already learned that the difference in various state of matter is due to the difference in the distances between the constituent particles. So what will happen when we start putting pressure and compress a gas? So enclosed in a cylinder, will the particles come closer? Do you think that increasing or decreasing the pressure can change the state of matter? Do you think? Let's see. So first, this is a piston, right? Or this is a cylinder. Now, by applying pressure, particles of matter can be brought close together. So these are the particles. Here you can see one particle here, one here, one here, one here. They are not close. They are existing in a gaps. Very much of gap. Here is a gap. Here gap gap. So we are giving pressure, and see this. We are giving pressure and and making them to stay close to each other. Right. This. So applying pressure and reducing temperature can liquefy gases. Okay. So applying pressure and reducing temperature can liquefy gases. Have you heard about solid carbon dioxide, CO2? It is stored under high pressure. Solid CO2 gas converted directly into gaseous state on decrease of pressure to 1 atmosphere without coming into liquid state. Okay. So they are saying solid CO2 gets converted directly into gaseous state. Okay, solid CO2 gets converted directly into gaseous state on decrease of temperature. If you decrease the temperature, it is directly become gaseous from solid. There are no liquid state here, CO2. If we decrease the pressure to 1 atmosphere. So without coming into liquid state, this is the reason that solid carbon dioxide is also known as dry ice. Thus, we can say that pressure and temperature determine the state. We can say that, right? So we can say that pressure and temperature determine the state of a substance, whether it will be solid or liquid or gas. Whether it will be solid, liquid or gas, okay? So now, so now, so now, so so now let's go to that. So now here is thus we can say that pressure and temperature determine the state of a substance, whether it will be solid or liquid or gas. We can say that pressure and temperature. So we can say that pressure and temperature are or will be determine the state of a substance, whether it will be solid, liquid or gas. So here you can see the image. So first solid. So solid fusion became liquid, vaporized become gas. Then gas deposition became solid. Solid deposition became solid. Also we can call solid sublimation became gas. No liquid is formed. Sublimation, decomposition also there is no liquid. Now liquid solidification they become solid. Liquid condensation became gas. Sorry, liquid vaporization became gas. Gas condensation became liquid. So interconversion of three states of matter. Now star mark. So atmosphere ATM is a unit of measuring pressure. Atmosphere is unit of measuring pressure extended by gas. This unit of pressure is Pascal. So atmospheric pressure or gas we the unit of pressure is Pascal, PA. Unit of pressure is Pascal, always remember. So 1 atmosphere equal to 1.01 into 10 to the power 5 Pascal. So 1 atm equals to 1.01 into 10 to the power 5 PA means Pascal. So the pressure of air in atmosphere is called atmospheric pressure. So the atmospheric pressure at sea level is 1 atmosphere and is taken as the normal atmospheric pressure. Right? Yeah. The atmospheric pressure at sea level is 1 atmosphere and it is taken as normal atmosphere pressure. So now questions are convert the following temperature Celsius scale, the 30K, 23K, 300K and 573K. What is the physical state of water at 250 degrees C and B 100 degrees C? For any substance, why does the temperature remain constant during the change of state? Suggest a method to liquefy atmospheric gases. Evaporation. Do we always need to evaporation? Do we do we always need to heat or change pressure for changing the state of matter? Can you quote some examples from everyday life where change of state from liquid to vapor takes place without the liquid reaching the boiling point? Water, when left uncovered, slowly changes into vapor. Wet clothes dry up. What happens to the water in the above two examples? So we know that particles of matter are always moving and are never at rest. At a given temperature in any gas, liquid or solid, there are particles within different amounts of kinetic energy. In the case of liquids, a small fraction of particles at the surface having higher kinetic energy is able to break away from the forces of attraction of the other particles and gets converted into vapor. This phenomenon of change of liquid into vapors at any temperature below its boiling point is called evaporation. So where are we? In the case of liquids, a small fraction of particles at the surface having higher kinetic energy is able to break away from the forces of attraction of other particles and gets converted into vapor. So this phenomenon of change of liquid into vapor at any temperature below its boiling point is called evaporation. So factors affecting evaporation. Let us understand this is with the activity. Okay. Take 5 ml of water in a test tube and keep it near a window or under a fan. Take 5 ml of water in an open china dish and keep it near a window or under a fan. Take 5 ml of water in an open china dish and keep it inside a cupboard or on a shelf in your class. So record the room temperature. Record the time. Record the time of days taken for the evaporation process in the above cases. Repeat the above three steps of activity on a rainy day and record your observation. What do you infer about the effect of the temperature, surface area, and wind velocity, speed, or evaporation? So you must observe that the rate of evaporation increases with so an increase of surface area. We know that evaporation is a surface phenomenon. If the surface area is increased, the rate of evaporation increases. For example, while putting clothes for drying up, we spread them out. Okay. For example, while putting clothes for drying up, we spread them out, right? So wet clothes, wet when we washed clothes, these are wet clothes, right? For wet clothes, for them to dry, we spread them in sunlight so they can dry up, right? So the increase of temperature, more number of particles get enough kinetic energy to go into the vapor state. A decrease in humidity. Humidity is the amount of water vapor present in air. Okay. The air around us cannot hold more than a definite amount of the water vapor at a given temperature. Okay. So if the amount of water in air is already high, if the amount of water is in air is already high, the rate of evaporation decreases. An increase in wind speed. So an increase in wind speed. It is a common observation. It is a it is a common observation that clothes dry faster or a widely day. It is a common observation that clothes dry faster on a windy day. Okay. Clothes dry faster on a windy day with the increase in wind speed. The particles of water vapor moved away. Water vapor moved away with the wind, decreasing the amount of water vapor in the surroundings. Okay. How does evaporation cause cooling? So in an open vessel, the liquid keeps on evaporating. The particles of liquid absorb energy from surrounding. Liquid keeps on evaporating. Okay. The particles of liquid absorb energy from surroundings to regain energy lost during evaporation. This absorption of energy from surroundings make the surroundings cold. So now what happens when you pour some acetone, nail polish remover on your palm? The particles gain energy from your palm or surroundings and evaporate, causing the palm to feel cool. After a hot sunny day, people sprinkle water on the roof or open ground because the large latent heat of vaporization of water helps to cool the hot surface. So can you cite some more examples from daily life where we can feel the effect of cooling due to evaporation? So why should we wear cotton clothes in summer? So during summer we we perspire more because of the mechanism of our body which keep us cool. We know that during evaporation, the particles at the surface of liquid gain energy from the surroundings or body surface and change into vapor. The heat energy equal to the latent heat. Energy equal to the latent heat of vaporization is absorbed from the body, leaving the body cool. Cotton being a good absorber. Cotton being a good absorber of water helps in absorbing the sweat and exposing it to the atmosphere for easy evaporation. Okay. So what you have learned? Why do we see water droplets on the outer surface of a glass containing ice cold water? So let us take some ice cold water in a tumbler. Soon we will see water droplets on the outer surface. Water droplets on the outer surface of the tumbler. The water vapor present in air on coming in contact with the cold glass of water loses energy and gets converted to liquid state, which we see as water droplets. Why does a desert cooler cool better on a hot dry day? Why does a desert cooler cool better on a hot dry day? How does the water kept in an earthen pot matka become cool during summer? Why does our palm feel cold when we put some acetone or petrol on perfume on it? Why does we able to sip hot tea, milk faster from a saucer rather than a cup? What type of clothes should we wear in summer? So what you have learned? Matter is made of small particles. The matter around us exists in three states: solid, liquid, air, gas. The force of attraction between the particles are maximum in solids, intermediate in liquids, and minimum in gases. The spaces in between the constituent particles and kinetic energy of the particles are minimum in the case of solids. The spaces in between the constituent particles and kinetic energy. The spaces in between the constituents, particles and kinetic energy of the particles are minimum. Okay, minimum in case of solids. Okay, kinetic energy of the particles minimum in the solids, intermediate liquid and maximum gases, because that's why gases particles are moving very fast. The arrangement of particles is most ordered in the case of solids. Arrangement are most orderly managed. In the case of liquids, layers of particles can slip and slide over each other, while for gases there is no order, particles just move about randomly. The states of matter are interconvertible. The state of matter can be changed by changing temperature or pressure. Now, sublimation in change in the chain. So sublimation is the change of solid state directly to gaseous. What is sublimation? Sublimation is when a solid directly changes to gaseous state, we call it a sublimation without going through liquid state. So deposition is the change of gaseous state directly to solid. What is deposition? Deposition is the gas state directly to solid state. Gas state directly to solid state without going through liquid state. Deposition. Boiling. Boiling is a bulk phenomenon. Bulk phenomenon. Particles from the bulk whole of the liquid change into vapor state. Boiling is a bulk phenomenon. So particles from the bulk whole of the liquid change into vapor state. Okay. Change vapor state. So evaporation is a surface phenomenon. Evaporation is a surface of phenomenon. The particles from the surface. Evaporation is surface of phenomenon. Particles from the surface gain enough energy to overcome the forces of attraction present in the liquid change into the vapor state. So what it says particles from the surface gain enough energy to overcome the forces of attraction present in the liquid and change into a vapor state. Okay. The rate of evaporation depends upon the surface area exposed. The rate of evaporation depends on the surface area exposed to the atmosphere, the temperature, the humidity, and the wind speed. So evaporation causes cooling. Right? Evaporation causes cooling. How? Evaporation. If I want to know how evaporation causes cooling, can you tell me? Evaporation causes cooling how? Tell me how evaporation causes cooling. So, so how it works? High energy molecule escape. In a liquid, molecules are constantly moving. Right? In a liquid, molecules are constantly moving. The ones with higher kinetic energy can break free from the liquid surface and evaporate into air. Higher kinetic energy means it has a higher kinetic energy. The ones with higher kinetic energy can break free. The ones with higher kinetic energy can break free from the liquid surface. Higher kinetic energy can break free from the liquid surface and evaporate into the air. Energy lost from the liquid. When these energetic molecules leaves, they take away heat energy with them. Okay, so they take away heat energy with them. That's why we feel cool after getting evaporation. So average energy decreases. the remaining molecules have lower average kinetic. So average energy decreases here saying the remaining molecules have lower average. Remaining molecules have lower average kinetic energy, right? Which which means the liquid's temperature drops.